who is yeah, is it, it's okay. Okay, all right. Okay, all right. Okay, yeah. हाँ जी. Okay, anyone whose email I'm missing? Okay. Oh, you can share? Okay, okay, all right. Yeah, I don't, yeah, please share. Let me just share, and then the ones who haven't received, please share. Okay, so maybe this is the overall structure of the files. So I have tried, I should say, like my student and I have tried to do all the analysis in this, like through Google Colab. The first one is what I had given you. And then the second one, which we'll cover today, is like reading through the file, writing, plotting, and then finding the dimension, reading the header information, and things like that, right? And then we have task data processing, how to process task data. And then I hope to do these two today. And then tomorrow is Wednesday, so tomorrow I'll try to do the resting state. And then Thursday would be ICA. And then I'm trying to think what is the best way. Perhaps on Friday I will do 5A, but then one thought I have is that have you try 5B as your assignment for the weekend and next week, right? So most of the methods has been described till 5A, right? We have like how to do ICA, how to do correlation-based analysis, how to do quality control. So all of those have been described in the first 5, right? And then 5B is what you would be doing using autism data, right? And so for autism data, you will have 100 subjects and you can analyze them, right? And I would like all of you to try different methods and see whether you can identify any differences, right? Again, I should emphasize that, you know, once you go through this, then it's fairly, well, nothing is easy, but it should not be very difficult to try another data set, right? So instead of autism, if you wanted to do Parkinson's, then you just need to you can use the same structure, and then if you put the Parkinson's data, then it will analyze the data for you, right? Right. Okay, so just to reiterate, the first one, everyone, I think this, okay, yeah. So this is the first one, right, where you copied the file, right, created your own directory, and then downloaded into that directory, and then you used simple commands um, to access your drive, and then you used installed these libraries, right? Babel, NumPy, and Matplotlib are common packages which are used for like medical imaging analysis, especially for fMRI, right? Is there anyone who hasn't been able to do the first part? Anyone? Okay, if so, if someone hasn't done and is not speaking up, I'm pretty sure I'm going to lose you for the rest of the course, right? Okay, so I'm assuming all of you read through this. And so this one is D1B. So do all of you have access now to this? I would suggest you to also, we can all run together, right? And then see what happens. And if there is some issue that you face, I will try to help you run through them. Okay, so the first, again, like each time we have to run this. Again, this is accessing our drive, right? The Google Drive. And I'm guessing most of you should have enough space in your Google Drive to download the data. Uh, yeah. Huh? Right. Okay. Could someone share it with Rahul? Or else, okay, just 1 second. I can do that. Sorry about that. Rahul Sharma, right? Joshi, sorry. R. Yeah, my computer is for some reason very slow. Okay, RJ 2393. Ah, yeah. Okay. 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 Again, anyone who hasn't received, let me know, I'll share it. And all of you, please run through this one, right? And as I mentioned, this simply, like, you have put the data in the Google Drive, and this is accessing. I don't know why it's taking so much time. Okay. All right. So the drive has been mounted. And again, as I said, if you, let's say, had a different data set, you can, delete the data which is here now and put the data, and then depending on the folder that you are accessing, you should be able to access, right? And NIBabel and NILearn are new neuroimaging libraries which are used. And then for plotting, right, we use matplotlib, and NumPy is a very standard scientific package which is used in Python, right? So now I install them. Okay, it's done, right? And so I have installed the libraries. I have like Google Colab now has access to my data. So I can simply now run to see what is in my data, right? So ls is list the files, and then it goes to data, the raw data, subject one, anat, and it says that the data is this one, right? Did everyone get this? Yeah, everyone? Yeah. Okay, and everyone knows how this is done? Can anyone find the file size? How big is this file? Can anyone tell me the command? Everyone is getting this? Anyone who isn't, who is having trouble? I will just check. The data pre-processed folder does not have right. On the yeah. So once we run the command for the directory, yeah. So should we make a folder on that directory? You should make a folder in your drive. Okay. Which part are you in? Okay. Good. All right. Okay. Okay, not everyone is up to date, but it doesn't matter to me. So I had asked several times. Okay, so if I want to see the file size, right, I can just do this, ls minus L, and it will tell me the file size is this much, okay? And again, these are commands within ls that you can use. But for simplicity, I just wanted you to see, as you look through the data, how much, like what is in which directory, right? And if I wanted to find out what is in what directories are inside something, then I could type star, and it will show that subject 1 has under anatomy this file, and in functional these 4 or these 5 files, okay? And so the 5 files are task motor run 1. This is the event file when the subject performed different tasks. Task motor run 2, the event file, and then there is resting state, right? So there are 3 runs, like 2 motor task, 1 is resting state. Okay. Again, I think I would, well, once you are able to replicate this, I would encourage you to play around with it to get a better understanding, right? Then I want to see how does the structural image look like, right? So here I provide subject name is this, anatomical file path is data raw, subject name, then anatomy, subject name, session structure, right? Run 1. And then I want it to load it. This is the function from the libraries that we installed, right? NI Bible, NIBable, and then I want to print this data, right, which is the anatomical data. And when I print, what I get is the data shape, which is the dimension of the data, which is 224 by 256 by 256. So it is like a 256 by 256 matrix with 224 slices, right? So that is the 3-dimensional data. And these are typically not used, but these are good information to have, right? The size of the header, then these are the dimension. Again, 224, 256, 256. And then these are the way the data is stored. This is the data type, right? Float 32. And then the slice start is 0, right? Again, this is important because in MATLAB, the first number is 1, while in Python and C, the first is 0. Okay. Second, yeah, the second is, the other thing is pixel dimension, which is the voxel dimension, right? Which is 0.8, 0.8, 0.8. So these are, in this case, not you had a question? Someone, okay. So these are the information, but typically these are the features or the parameters that you should remember, like you should be careful, like it should be float 32, If it's integer, then it will give a lot of trouble. Then you should know the voxel dimension, and then you should know the matrix dimension. Okay. Right. So this is what we say. The output you see after loading the Nifty file with nib.load is an object of the nibable nifty.nifty image class. This objects hold all the information about your loaded neuroimaging data. And these have been broken down into the following class, right? This confirms that the loaded object is a Nifty1 image object from the nibable library. The data shape is 224 by 256 by 256. This indicates the dimension of the image data. Since we have loaded anatomical data, it is a 3D image, right? And so the dimension will be X, Y, Z. So these are like the main things to remember. And I also told you how you can find out the size if you want, right? So the next thing is we want to extract the image as NumPy array, right? So once we have read the image, right? So it reads the data and then it basically displays the data in a numerical form, right? So again, this is 224 by 256 by 256, and that's how the data looks like, right? We cannot visualize or cannot comprehend how the image looks like just by looking at the data. And so what we have to do is we have to visualize the data, okay? So far clear, everyone? Okay. So as I had mentioned, like any image is nothing but a matrix of numbers, right? Any image is simply a matrix of numbers. And so this one was a 3D matrix of numbers. Now what we want to do is display these images, okay? Okay. So what we are trying to do is we are importing matplotlib as plot. And then what we want to do is display these images, right? And because we have 224 images, sorry, 224 slices, what I want to do is just display slice number 50, 100, 150, and 200, okay? And further, so I have 4 variable, 50, 100, 150, and 200. So those are my Z values. Also, I want to display them as grayscale images, right? And then I want to plot them, and the title would be the slice number, okay? And if I run this, it shows the axial slice number, right? This is slice 50, slice 100, slice 150, slice 200, Okay, so far everyone is clear. So far everyone is able to generate this. Okay, so because we have to give you grade at the end, can you take a screenshot and email me what you have? Okay. Yeah, now. So while you are emailing me, what do you think about the slice number? Slice number 0 is at the bottom of the brain or top of the brain? Bottom, right? Anyone who disagrees? Okay, good. Um, so it starts from 0, 1, 2 till 224, right? So after you have done this, maybe just as a test, try maybe 0, 50, 100, and 150, and show me how it looks like, how the images look like. Right, so in this case, in here, I have provided 4 different values: 50, 100, 150, 200, right? So I want you to try 0, 50, 100, and 150, and show me how the image looks like. Okay, good. Yeah, yeah. There is no time information. Right, right. So again, so okay, that's a good point. So this is not resting state data. This is the anatomical data. The the functional data. There are 3 functional data. One was motor run 1, motor run 2, then resting state. This is the anatomical data. First, the anatomical data dimension is, it's a 3-dimensional file, right? While the functional data will be a 4-dimensional file, right? So this one, um, this is how we have displayed, and by changing with these numbers, you can display any slice that you want. Right, yeah. No, this is for one run. Just the anatomical, not run, just the anatomical, right? Right, because previously we looked at the anatomical data, ANAT, right? The ANAT data. Okay. Anyone else who was able to do it for 0, 50? You were able to? Can I see the screen? Good. Very good. Okay, great. Okay, so this is the way. So this is the way in which you can display different slices, right? You can take any image, read it, and then display it. It doesn't have to be MRI images. If you want to download, your photo, you can also use the same function to read it as a JPEG or TIFF file, and it will work, right? So then what we want to do is that while this looks okay, sometime you want to display by rotating, right? And in this, with NumPy, the rotation is very simple. np.rotate 90 is going to rotate your images. So in this case, if I run this, right? So the same information, the only difference here is that NP rotate, we simply rotated the images, right? Also, again, if you have time, instead of grayscale, you can try other kinds of like color scheme, right? Okay, so everyone is clear. So yeah. So you can, instead of gray, you can try like hot, right? So like almost like, do you use MATLAB? So if, okay, so if you use MATLAB, you can check what, there are many different ways you can use, many different function color schemes, and you can easily, yeah, yeah. So you can try. Okay, everyone is clear so far, right? Right. What happened? Right, right. Right, right. Yeah. So flip. Yeah. All right. Okay, so everyone is clear how to do this. So let's say I wanted you to, instead of displaying axial slices, I wanted you to display sagittal slices. Will any of you be able to do that? So maybe you can use it as a like as a homework, right? So this one is in axial. Try to also display in sagittal and coronal, right? Like do it as a homework, right? So again, here, right? So here, there is some homework for you that you can try, okay? Write your code here. So that's your homework, right? So while I showed you how to do axial, write the code for sagittal or coronal, right? Once you do sagittal, it should be straightforward to do coronal, okay? Any questions? All right. Okay, so we first did the anatomical. Now we want to look at the functional data, right? And if I want to look at the size, then I just do this and I can see the size of the files. Okay, this is the motor functional run 1, this is motor run 2, and this is the resting state. So we have 3 functional files, right? 1, 2, 3. 2 motor, 1 resting state. So this is plotting the information about the resting state data. So the anatomical data was 224 by 256 by 256. What is the dimension of this data? It is 64 by 64. So 36 slices and 818 time points, right? So that is the temporal dimension, right? So again, by using this command, you can read and you can get information about what this data type is, okay? So in this case, the previous one was float, right? In this case, okay, so these things you have to be very careful. And the spatial, the pixel dimension is 4 by 4 by 4. What is the TR? What is the sampling rate? Repetition time? 2.2. Good. Right. So the functional file is 64 by 64 by 36 times 818. Unlike the anatomical data, which was 3D, the functional data is a 4D file. The first 3 dimension 64 64 by 36 representation represent the matrix along the x, y, and z axis, while the 4th dimension represent the number of time points, right? And the other things like integers 16. The one other thing which sometimes is critical is how the data is acquired, right? And this says slice code. This indicates the slice acquisition order. In this case, alternating, increasing 2, right? So it would be slice 1, 3, 5, 7, 9, 11 till 35. Then it will go to 2, 4, 6, 8 to 36, right? So that is the data order. And in this case, because we have only 36 slices, we are trying to display in a similar fashion across 5, 10, 20, and 30. Right, again, these are much faster than in MATLAB. It's like to run this, it took like 4 seconds. Right, and you can display this. And again, the code is very similar to how we had displayed the anatomical. Right? Can anyone tell which time dimension did we use? Okay. So as we visualize both the anatomical and functional slices, you can see the difference in spatial resolution, right? Although we are acquiring fairly similar slices, while this is the axial images for the functional, these are the axial images from the anatomical, right? So you can see a big difference in the clarity, right? Here, the spatial resolution is 0.8 by 0.8. In here, the spatial resolution is 4 millimeter by 4 millimeter. So we are gaining temporal information by sacrificing the spatial information. Similarly, we can do other tests or other things, like here we can compute the mean, again using NP mean functional data, and it will compute the mean, right? Again, it's really fast. And then, if we want to right, you can do this. And then what we can do is we can process the data and use affine transformation of the functional data such that we can compare with the anatomical data. Right? So here what we are doing is we are averaging the mean using affine transformation and saving this. Right? And so with Nylon and Nibable, you can use different features. And one of the useful features is how to plot these data, right? So we install Nylon. Right, so it installed. And then you can use Nylon plotting function to plot. And then it shows different ways in which you can display orthogonal slices across sagittal, coronal, and axial. You could also use like as a mosaic, right? Slice 1, slice 2, slice 3. Or you can also use across different dimension. And the last function is to display it as a glass plane. You can define the opacity and the translucency of the brain. This is particularly useful when you want to display functional information on the anatomy. So you can make, depending on what you want to do, you can make parts of the anatomical brain like visible such that someone can see where in the brain there is activation. So this is one way to display the orthogonal structures, the 3 orthogonal plane, right? So for any location, it would, right, in this case, we gave the coordinates, and then, so this is the coronal slice, this is the sagittal slice, and this is the axial slice. And the cross here for each of these location is the same voxel. Okay, so you can basically click around if you want to in different packages, and then by clicking here, this would automatically change. Right? So this is orthogonal plotting. This is like mosaic or montage, right? So where you want to see all the slices or a few of the slices in different orders. Right? So this is axial, this is sagittal, and this is coronal, right? So again, if you are to display different slices, then you can use this function to display them. Okay. Again, we are trying to do the same thing with anatomical, right? We are also plotting them in an orthogonal plane. Right? Right, so again, coronal, sagittal, and axial. Right, so there is a homework for you here where you have to do the anatomical mosaic plot, right, just like we did for functional. Can you, what is the time? Oh, 3 o'clock. Okay, you could, okay, you can try it. You can try it later. Because the code actually is here, right? You just need to modify the code, which I did for functional. You try it for the anatomical, right? And then run the code. You should get similar results, okay? The next is, you know, if we can plot the anatomical and functional to see how the overlay, right? So this is displaying the functional image on the anatomical. Right? So again, the background is the anatomical, the green is the functional, right? Again, this looks like this because the functional, the signal from here is very low. And we are also plotting this because we want to make sure that the anatomical and functional are well aligned, right? Because when we compare across different brains, we transform the anatomical into the MNI template. Like MNI is the average brain, which is transformed. But before that, what we do is we use affine transformation from functional to anatomical, right? So that they are well registered. Then we register the anatomical to the MNI template and then use the same transformation to transfer the functional to the MNI template. Okay. So this is another way to check if the subject has moved between anatomical and functional, right? If the subject had moved, then there would be a mismatch, right? So, you know, in my humble opinion, you should spend a lot of time doing quality check about your data, right? Before you do any analysis, because all these things, if you don't check now, when you check later, you have to redo everything, right? So this is a part of quality check, right? So this is one way to look. The other way is to, check for co-registration, and by visualizing this in terms of how much change that is occurring, right? Again, so in this case, so anatomical image contours on functional data, right? So this is like another way to look at the data. But in here, one has to be careful, right? Because if there is a signal dropout, it can affect these changes, right? Okay, so this is like, I hope this is like ways in which you can look at the data, read the data, find the dimension, and do like very basic analysis, like I shouldn't say basic analysis, like basic QA, right? Like, is the anatomical data and functional data properly aligned, right? Is there any artifact which is present in the data, right? Is there signal dropout in the data? So all those things you should look at this stage, right? Any question? Okay. So I'm just going to, okay. So you have assignments in this one that you have to send me. Okay. I think Dr. Bhumika mentioned that there is an exam that's going to happen, but maybe I think that's a great idea. Yeah, but we, work hard not to get a B, right? Okay, we can ready for another hour. Like we can continue, right? Okay, maybe I can stop now. And if you have, yeah, if you have any questions, like like uh, ask, right? I should say I spend a lot of time on working on the Google Colab because I primarily write codes in C and MATLAB and not in Python. And I think after Dr. Bhumika mentioned that I should avoid MATLAB, I thought, okay, this is my chance to learn Python. But I think it's working on it has given me a lot of ideas for classes, but I think also for now for publications and so on. Maybe now I can just have a Google Colab and then just have figure 1, figure 2, and someone just needs to press the button and the figures would be generated. Right, no questions? Okay, so if no one has question, let me ask you. So if I showed you how to do axial, how would you do sagittal? Okay, I think she was starting, say first. Okay, how were you saying? I didn't understand. So you have, okay, so you have a three-dimensional data, right? And you were, okay, let's go back. Um, okay, so in this case, where are we displaying the axial images? Very good. So PLT I am show colon, comma, Z, right? So colon, colon, which is 256. Okay, did you try? And it worked? Can you show? How many slices? Okay, just plot one slice, if like such that everyone can see. Right, so as she is meant, yeah, sure. Okay, um, I, I, I believe you. I think I can see it. Okay, good. Um, so this is the line which you have to um, modify, right? So colon, comma, Z is axial. So for the other one, it would be z comma colon comma colon. The other one would be colon comma z comma colon. Okay. All right. Okay. So can anyone, right? So if I told you that, okay, for the 4D data set, I will give you coordinates for X, Y, and Z, but can you display the time series? Can anyone do? Can anyone plot it? Think. Okay, think. Huh? So you have a 4-dimensional data set. You have X, Y, Z, and time, right? So I will give you X coordinate, Y coordinate, and Z coordinate. I want you to display it as a time series. How does the signal change as a function of time, right? So let's say X equal to 32, Y equal to 32, and Z equal to 16, right? Can anyone plot the corresponding time series? Abhishek? You can try. Sanjita, you can do it. How does it look? You could? All right. Maybe lift it, make it intensity brighter. Okay, so this is how Shreyansa's looks like. I think they could not see. Okay. So then you can try. So what command did you? Okay. Good. So you can display in 2D, or you can also display 1D. Okay, it's 3:15 now, or 3:13. Okay. Shreyans, can you just? Oh, right. So the question is that here, okay, not here. Here, I displayed slices, right? For different slices, I displayed the images, but instead of the slices, if I had told you the coordinates and asked you to display the time series, the 818 time points for any given voxel, would you be able to display that? You can make up. So I think I had said 32, 32, and 16. Okay, so maybe before you go for your break, one thing to try is like download, okay, not download. So run the first 3 commands, right? This will take a few minutes, but the FSL takes like 10 minutes. So like run, Okay. So we will be using FSL, and this is the one which took, like when I checked, it took 10 minutes. So maybe you can run it before you go for your break. I guess this is the good thing, as this the bad thing about Google Colab is that you have to install these things every time you want to run. Oh, you okay? All right. Okay. So we take a 15 minutes break. Yeah. Really? In the task processing. What is the error?
So here, what Pratik did, Pratik has defined these two variables, and so basically they are extracting as an object.
Yeah.
And in the next section,
Yeah.
he has called it as a function.
Right.
So object cannot be called as a function.
Oh.
So that's the only thing. We just have to change the variable.
Okay. Okay. Okay.
कप में दे दूं?
ठीक है. काफी है. Thank you. No one wants to go for a break. No one wants to go for a break. Wow, that's dedication. Right?
So they are saying remove any previous installation, and I don't want to install it because I am working with it and I have a lot of data.
Okay, okay.
So I don't want to. I don't want to do a.
Right, right. Okay, I understand. Mm, mm,
Is it possible that if you go, suppose if you use command and I use my interface interface?
right, right. It should be okay. It should be okay. I mean, the other thing you could do is comment the RM minus RF, comment this out.
The local.
Yeah, yeah. ICA is a very commonly used method to find the components. So I hope we can cover some of the tasks today, and then tomorrow I would cover resting state and ICA. All right. Okay, so I have installed, like, this is the command to install FSL. I think it's the longest. It took like 11 minutes, and after that, like, you have to, check if FSL is correctly installed, right? Which Yeah, if those of you have FSL on your computer and you are using for other things, then maybe don't install FSL, and try to run and see whether it runs. Let me know what you get, because I can try to figure out what could be happening tonight and let you know tomorrow. Okay, so that's okay. Yeah, because like the command you should be able to use regardless. Again, this is just a way to use. Like again, maybe I should just say that how many software packages do you know for analyzing fMRI and MRI data? CAT is a part of SPM. Right, MATLAB SPM, then there is FSL. Anyone else? Okay, yeah, FreeSurfer. You use Brain Voyager? Okay. Okay. Anything else? I thought I heard someone mention the word con. You use con? Oh. Okay, all right. So con is also good to analyze. There is also another package called AFNI. Like, I would say that all of them are very, very similar. If you become good at one, perhaps you can easily learn the other feature from other ones. The way I analyze the data is that I use like AFNI is good for certain things, FSL is good for certain things, SPM is good for ANAT and things like that. So depending on what you're interested, you could write another script which would be calling different functions from different things. But to do that in Colab, I don't know enough about Colab to do, so I just focused on FSL. Okay, so then we will look at, we will pre-process one subject. So this is subject one, right? Actually, this is publicly available data. So again, if after you try some of this, you can add more subject. This is called the Midnight Scanning Club, which has, is it 10 subjects? I think it is 10 or 12 subjects. Each of these subjects have been scanned more than 10 times, right? So, and each time the resting data is about 20 to 30 minutes long. So fairly good data for reliability testing. Okay, so right, so it processes the data. So one thing we want to do is we want to extract the brain using BET command, right? So that is a command which would mask the data, right? So it would mask the brain and it would make everything outside the brain into a zero, right? So this way we can do certain things, right? We can increase our computation much faster because like we can only process data which is inside the brain and exclude um, voxels outside the brain, right? Yeah, yeah. Right, right. Right, right. I okay that right, right. Again, that's I admire your honesty. Um, and I again like writing uh, GUI is not that difficult, right? But in my humble opinion, it is good to know how each of these commands run, right? And once you know how the command runs for a few subjects, then you should use the GUI, right? Otherwise, what happens is if if you run through a GUI, you may not understand the inner workings of how each program is running, what are the variables given, um, and what are the maybe the underlying assumptions. Right, 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 right. I couldn't have said it better. That is what I'm trying to say is that um, there are GUIs, right? Like SPM is very popular because it's GUI driven. FSL is also very popular because it's GUI, right? AFNI, like Con has very even better GUI interface, but AFNI doesn't have a good GUI interface. But many people who like write program and so on, they use AFNI, and they're like, and even when the app, so the way AFNI was written, um, the idea is that you should understand the data, and you should understand the data on a subject to subject level, right? Um, so you can you can use any of these software packages, but I feel it would be it is good to know how the data is processed, and then you can write GUI. You could also write scripts, right? Once you have this, maybe you can ask Gemini to write a script where you have not 2 subjects but 20 subject, and I think it can easily write a script for you, right? Yeah, yeah, yeah. um, okay. I would say try. Like if you cannot, then let me know, and I can point out to how it can be done with GUI. Okay, so right, right. So these are the orthogonal anatomical images, and then this is after using brain extraction. Right? So the skull has been like eliminated. Anything outside the brain is a zero value. Only voxels inside the brain have non-zero values, right? And again, as I said, this has several advantages. Like in other packages, like in AFNI, this like instead of BET, it is called auto mask, right? It will create a mask of the brain images, right? And then what we can do is we can look at anatomical after it has been automasked, displayed on the original anatomical image. Right? So again, because this has color and opacity, you can see how well these things match. And it's not surprising because it's a very simple function to find voxels outside the brain and make it zero, and make voxels inside the brain be their original values, right? So again, like what we have described here is how you can change the intensity values using different parameters, and then test these parameters, right? So the next thing is motion correction, right? As I mentioned earlier, the biggest challenge for fMRI is head motion, right? How much a person moves. And in FSL, the command is called McFlirt, right? MC flirt. And these are the usage, how to use McFlirt. And again, like these are the things. It would be good to know what kind of registration you can do because it has so many parameters. When you're doing a GUI, generally the default is used, which may be okay for many cases, but not all the cases. And then we do the, right, so it does the registration, right? It's going to take a while because there are, you know, many slices and many time points which are there. So it will run through all those data set. And so it corrected for the motion parameters. And then we want to see these files, so we can see these files which have been created. So this is the motion corrected file, right? And it is a 4D fMRI data. And this is for the motion corrected for the task motor run 1, right? And then we want to see how much motion this subject had. Right? The contrast is not very good in this. Again, suggesting that maybe the motion in this data was, what happened? That the motion in this data was reasonable and was not high to be highlighted in any specific region, right? And then what we can do is then visualize the motion parameters. So these are X, Y, and Z motion parameter, again for the task 1 run, and these are the rotational parameter, right? So by looking at this, can you say anything about head motion? Did the person move the head? Right. Good, right? So, so that is how we can look. So this is the translation in millimeters, and it is less than 0.15. And even this periodic one may not be head motion per se. It could be respiration signal, right? So the head motion, this is like what we call a good subject, right? Although during rotation we see a jump here, right? But it shouldn't matter that much because the motion doesn't seem to be much, right? So when we are looking for motion, what we are looking for is sudden large changes in amplitude, right? Sudden large change in signal amplitude, which is more than, let's say, 0.3 or 0.4 millimeter, right? If it's more than 1, then we would have to look at the subject like individually, right? Right, right. So again, that's a very good question. How can we differentiate motion from the task? There are certain tasks, as I had mentioned, like for certain tasks, when you perform the task or the task condition is such that you would either voluntarily or involuntarily move. If you were getting a pain stimulus, maybe your body would stiffen up a little bit, and that is large enough to cause a head motion. or it could be, as I'm mentioning, if you are lying in the scanner and someone asked you to tap and you did like this, that is going to induce some head motion. So one has to be careful. Um, there are ways, so now there are ways in which we can do real-time motion correction, right? As the subject is being scanned, you can estimate how much motion there is. There is like 10-15 seconds delay or maybe 30 seconds delay. Even if there's a 1 minute delay, it is still okay, because at the end of the scan, you would know whether you can use that data or not, right? And if not, you can ask the subject to try to lay still and then scan. Right, so there's another measure of motion called frame-wise displacement, and this is the parameter. So like this frame-wise displacement of 0.2 suggests that the data is fairly good, or at least the subject did not move much, right? So as we collect data for every subject, we should have this information, like the frame-wise displacement. Okay. So in this case, what we are doing is we are giving the reference file and then computing the data structure, and then we can look at the output. And then once it has been processed, so now we have processed, so we take the anatomical data, skull strip the data, we take the functional data, correct for motion, skull strip the data, and then we transform them into MNI space, right? MNI space is a standard space which is very widely used, and this is an aggregate of many subjects' brains. So it is like we are transforming to a common template where we can say that coordinate XYZ represent this region, or coordinate 237 would be this region of interest, because this is on a common template. Right, so this is the MNI template. So basically with MNI template, any given region has a specific, for any coordinates, we know what the anatomical region is. Okay. I know it's 4 o'clock. Give me like 10 more minutes. So then what we do is we are running this and transforming the data into MNI space. Right? So this is a linear co-registration to MNI space. It has the anatomical data which runs through this. It uses the pre-processed motion corrected data. right? Also, like the MNI template that is used here has a spatial resolution of 3 millimeters. And here, so again, like here, the cost is like when it performs the registration, it uses mutual information, right? There are other ways to do, but because the contrast between anatomical and functional doesn't match, therefore they use a mutual information. Mm. So maybe today, when you get a chance, do your homework from 1B and then just go through this and try to run through this. What kind of exam would you like? Not multiple choice? Multiple choice? What does MRI stand for? Uh, if anyone gets wrong, I'm going to cry. Mm.
Sir, so is it fine if I download the two data you have given?
Yeah,
01 and 02.
right.
And run it on my FSL for the task-based analysis up to ROI.
Yeah.
Along with the ESP files.
No problem.
So I just would like to know in your ESP file,
Yeah.
what are the conditions for which I can create contrast?
I think it's given in that, right? The TSV file shows where they had to do what kind of motor task. I think one is like they had to move hand, like feet, move the tongue. So they wanted to map out the homunculus. It's taking so much time. So also for your final, do you think you could present? Yeah. But how much time would we have? What happened? Right, right. But you choose the data. So, um, so we have the autism data, which is 100 subjects, and you could try whatever you wish. Like if you did on resting state, that would be ideal. But even in resting state, there are many different kinds of measures. You could do correlation based and see if there is a difference. You could also look at like ALFF, FALFF. There are these measures that you can try and see, right? The thing is that there are 24 students, 23. So if each student talks for 10 minutes, that's 240 minutes. That's 4 hours, right? That may be too much. So like, can it be like 5 minutes? Is 5 minutes okay? That's one option. The other option would be like, um, we can like maybe tomorrow I can randomly pair students, because if you work with your friends, there is not much point. We could randomly pair students and then you work with them and maybe then present for 10 minutes. Does that sound okay? Unless you really feel you have to work with someone. But then they would have like, then you would have a advantage, right? How would I know? You don't even like, it's like, okay. I hate coding. I, I, it's like, but this is what I have to do. Okay, so it finished. Um, Again, I think I feel like coding um, is not. I hope there is no computer science student here. It's like, it's not very interesting. It's like, if you want to do, this, all I want to know is how to get from here to here. Like what method I use doesn't matter, right? Ye- Excepting I don't like black box, right? I want to know how I get from here to here. I don't have to know what is the most efficient code, as long as I know the steps that is used to get from one point to the other. Okay, so this is the anatomical image on the MNI template, and then this is the MNI template contour on the anatomical image, right? So this looks pretty good, right? This looks pretty good. Also, I should say, like in terms of programming, I feel that now you have to know a little bit of programming, because once you know a little bit, you can just ask ChatGPT or something to, you know, um, make the code for you. But you have to understand something, right? So I use a lot of ChatGPT, Gemini, uh, like Claude, and so on, like with different terminals. And I say that, okay, this is the error I'm getting. Can you fix my code? And then they're pretty good at that, right? Yeah, yeah. So you can go like, so I have shared the like the main file. So if you go to day 5B, right, it has all the data. So maybe tomorrow after resting state, we can decide, we can make groups, and then you can decide what you want to do. Okay. Don't you think you would have a huge advantage since you know? Okay. All right. Okay. So I'm basically just going through the data set and transforming into MNI space. Again, this is doing the linear transformation um, of the anatomical data to the MNI data. So again, this is on the functional data. And again, like here you can see, this is of course a good subject, but you can see that the overlay, it's pretty good. Like this is functional image on the MNI data, and this is the anatomical data, right? And then there is linear warping to MNI space. There are also nonlinear warping, like FLIRT is for linear and FNIRT is for nonlinear warping. And depending on the application, you can use, okay, maybe try this so far. Tomorrow I'm going to, what time is it? Yeah, 4:17. Um, so this is the task design, how, like, so the TSV file has the task event file, and just maybe take a look. And so tomorrow we will go through this and then design the task signal and then display them, and then do the analysis and display the output. Okay, so this is the design matrix for left foot, left hand, right foot, right hand, tongue, and so on. And then we use the general linear model, GLM, and then we will be able to generate the task response, right? So I think I cannot do it in the next 10-15 minutes. It will take like 45 minutes. So please go through 1B and what I covered so far on for 2, right? And then we can do, okay. Any questions? No. All right. I know it's, again, if there is anything I can do to make the course more interesting, let me know. No questions?